Hello, student. So this is assignment 1, communication system, assignment 1, question 5. So I will try to do this. So first I will take this question. Okay. So this is communication system. Communication system. Assignment 1. Assignment 1, question 5. Okay. So I think this question is not much difficult. Okay. So you have a base station here. Okay. And user is here. One user is here. Okay. So when this base station transmits the signal to the user, the shortest path is 1 kilometer. Okay. And the longest path is 1.5 kilometers. No? So it may be a reflected signal like this. Okay. We don't know. Okay. So anyway, it is about 1.5 kilometer. Okay. So you want to find the corresponding delay spread. Okay. So this is shortest path. This is the shortest path, and this is the longest path. Okay. So delay spread, you know what is the delay spread. Delay spread is the arrival time of the last signal, last component, multipath component. Okay. Minus the first component, arrival of first component. Okay. Time for arrival, last component, minus time for arrival, first component. So this is the delay spread. You already know that. So we can find it. We know that the speed is equal to distance by t. No. So distance is equal to, sorry, t is equal to distance by velocity, speed. Okay. So here you are given the velocity, and here you are given the distance. So you can find this very easily. So the spread should be the arrival time for the last component. That means the longest component. So it is 1.5 by 3 10 to the power 8. Okay. So this is in kilometers. So you have to convert this for this into meter, plus the shortest path, shortest component, shortest the first component, 10 to the power 3 by 3 by 10. So so simplifying this, you can find the delay spread. Okay. So I hope this question is not much difficult. Okay. So I will go to the next one. Okay. So this one. Okay. So here we know that equalizer can suspend or minimize amplitude or phase distortion of a signal. We already know that, no? So here we have a channel. This is our channel. Okay, channel is given. and we are given the equalizer, and we need to find the coefficients, no, this weighting factors, A0, A1, okay, this one, no, step parameters. So these are weighting factor of the filters, okay. So we have to estimate this parameters, okay. So we will try to do this, okay. So first of all, I would like to remind you some basic fact, okay. The first one is the time shifting property of Fourier transform. Time shifting property of Fourier transform. This is for continuous time signal, okay, continuous time signal, okay. So I think you may remember this property, okay. So if we have a time domain signal xt, and if we get the Fourier transform of this xt, okay, so it may be xf, okay. And if we have time shifted signal, okay, or same signal, but it is time shifted by t naught, say t naught. So we will have e to the power minus j omega t naught xf, okay. So this is time shifting property of Fourier transform for continuous signal, okay. So we need we have to use this property to evaluate that question, okay. So the next thing I want to remind you that LTI system, linear time invariant system. So you know that if we given input signal xt, we will have the output yt. Say the impulse response of this linear time invariant system is ht. So we have yt xt convol ht, okay. So if you want to find the frequency response of this system, basically we have to get the Fourier transform for both sides, no. If we get the Fourier transform like this, okay. So we have Fourier transform of yt, let's say it is capital YF, okay. And you know that when we doing the Fourier transform for this convolution, so it will become a multiplication, no. So we have here, we have Fourier transform of xt into Fourier transform of ht. So here it is not a convolution, it is just a multiplication, okay, not a convolution. Here it is convolution, okay. So we have YF, okay. So Fourier transform of xt, let's say it is xf, and the Fourier transform of this impulse function, let's say it is hf, impulse response, okay. So we have the frequency domain of frequency domain representation of impulse response, capital HF. We can get YF by XF, okay. So this is called transfer function, frequency response transfer function, no. This is frequency response transfer function, okay. So normally we called it transfer function, okay. So this knowledge you should have, okay. Other thing is the distortionless transmission, okay. I hope you have learned this in your lecture session. Okay, so we know that basically distortionless transmission means distortionless transmission means if we send bit pattern or signal, okay, so if we receive the same pattern, okay, same pattern, but it can be shifted, okay, it can be delayed by time, no issue, and the amplitude can be constantly vary, okay. So maybe it is shifted and amplitude can be changed, but that change should be a constant, okay. So if like this shifted and if we get the same pattern with the shifting by time, it is okay. And amplitude also can be changed, okay, amplitude can be changed, but that change should be constant, okay, but that change should be constant, okay, it should be a constant. So if this happen, we call this distortion transmission, okay. So so we know that if we have a channel, okay, if we have a channel, okay, so this is our channel, and we can represent this channel as a linear time invariant system, LTI system, okay. So if we give an input, okay, so that means this is our transmitted signal, okay. So this is input to the channel, okay, that means this is our transmitted signal, okay, transmitted signal. So it is propagating through this channel and received, okay. So output of this channel is YT, okay, so that is received signal, okay. So this is the received signal, okay. So this is transmitted signal, and this is channel is LTI system, okay. So output of this LTI system, output of the channel is YT, that is our received signal. So we have XT transmitted signal and YT received signal, okay. So we say that this is distortionless transmission. This is distortionless transmission if YT, okay, is equal to Kx T minus Td, okay. That means this K should be a constant, okay, constant. So this K is amplitude factor, no, but it should be a constant. So this K can vary the amplitude of this XT, the transmitted signal XT, okay, but that change is constant, okay, and this will be a delay, and it also should be a constant, okay. So this delay also should be a constant, okay. So if this K is a constant and this TD delay is the constant, we will say that this is a distortionless transmission, okay. So this is the time domain requirement, okay. So this is time domain requirement, okay. This is time domain requirement for distortionless transmission, okay, distortionless transmission, okay. So if I get the Fourier transform of both sides of this, okay, so I will get the Fourier transform of both sides, okay. Fourier transform of kx t minus t. Okay, so say Fourier transform of yt, say it is capital YF. Okay, and the Fourier transform of this kx t minus td. So you know that this k is a constant, so you can get this k out of the Fourier transform, and you have Fourier transform of x t minus td. Okay, so you know that this x t minus td is the time shifted signal. Okay, so we have, for the time shifted signal, we have this kind of Fourier transform, no? Okay, so using time shifting property, we can write this as e to the power minus j omega tt. Okay, so here it is not t naught, it is td into capital Xf. Okay, so if I divide this xf and here the both side in xf, you will get yf and xf, and it is equal to k e to the power minus j omega tt. Okay, so what is this? Okay, so this is input, so this is output of the system frequency domain signal, and this is the input of the system frequency domain signal. So you will get here the transfer function, no? Transfer function of this channel actually. Okay, so transfer function, I will put HC, okay, to imply it is channel. Okay, so channel frequency response or channel transfer function is equal to Ke minus j omega t. So this is for distortionless transmission, no? So this is for distortionless transmission. Okay, so you know, so we can see that for distortionless transmission, our channel transfer function should be like this. Okay, so this is the magnitude of the transfer function, so it should be a constant. Okay. And this is the phase of the transfer function. Okay, this is the phase of the transfer function. Okay, so this is for distortionless transfer function. Okay, distortionless transfer function. So this is for channel transfer function for distortionless transmission. Okay, so I like to I think you have learned this, so please remember this thing also. Okay, and we know that, okay, we know that, okay, so when a signal transmitted through a channel, when a signal transmitted through a channel due to a multipath propagation, or maybe attenuation, okay, so some kind of due to noise, okay, so maybe some kind of impairment can be happen. Okay, so due to those impairment, the input, the transmitted signal can be distorted. Okay, so transmitted signal can be distorted. Okay, so we know that, okay, we know that so this distortion, okay, that distortion can be minimized or removed. Okay, so normally we have amplitude and phase distortion, delay distortion. Okay, so delay is always related with phase. Okay, so we normally say that amplitude or phase distortion or delay distortion. Okay, so this amplitude and delay distortion, okay, distortion can be minimized or removed, okay, minimized or removed by a equalizer, okay, by a equalizer. Okay, so say we have a channel like this, okay, so say we have a channel like this, SCF. Okay. So now this channel is not a distortionless channel, okay, so this is distorted distortion channel, okay, it is not a distortionless channel, okay. So this transfer function is for distortionless, okay, okay, this transfer function is for distortionless, okay. And this is now this channel we have distortion, okay, and if you use a equalizer, okay, if you use a equalizer, and let's say that it is the equalizer transfer function is HEQF, okay, so this is the equalizer transfer function, this is equalizer, okay, and this is channel. So now this both the channel and the equalizer will create distortionless transmission, okay. So if we have xt here, okay, so some distortion can be happen, and that distortion will be removed from this so here the distortion can be happen here, okay, within this due to this channel, okay, and that distortion can be minimized or can be removed by this equalizer, okay. So you will have again the distortionless output, okay. So if you consider this whole transfer function, this whole system, that means channel plus equalizer, okay, so let's say that is H, okay, so that whole transfer function, okay, should be equal or approximately equal to k e to the power j omega t, okay, okay, because now no distortion, no, because now no distortion, okay. So we know that this total transfer function is generated through this channel and from this equalizer, okay. So it is a cascaded system, no, it is cascaded system. So this HF can be write as HCF, this is the channel transfer function, into equalizer transfer function, like this, like this, okay. So I think you could understand these are not very difficult concept, okay. So all things can be derived by using a principal factor, no. So I hope it is not much difficult, okay. So anyway, so we can see that the total transfer function that generated through channel and equalizer can be expressed like this as a product of this channel transfer function and equalizer transfer function, because these are cascaded, because these two systems are cascaded. So it will, the transfer function, you will have a product here, okay. And you know that for distortionless, this transfer function should be equal to ke minus j omega tt. So this one also very important facts, okay, you should remember, okay. So now I think we can go for our question. Okay, go for our question. Okay. So here it is said that the signal is distorted due to multipath propagation. Okay, so we are given the channel model here. Okay, so this is our channel model. Okay, so I will use this channel model. Okay, so we know that this is our channel. Okay, so this is our channel actually. This is our channel. This is our channel. This is our channel. So that channel have two paths. Okay, so if you transmit the signal, okay, transmit the signal, let's say it is xt, okay, and here you will receive the signal, okay, and let's say it is yt, okay. So what is the yt? Okay, so here the signal is come through this channel, no, channel to the user. Okay, so this is base station and this is user. Okay, and you can see that the transmitted signal has two paths. Okay, one is just a delay, that means it is a line of sight path, and you can see that here additional delay also there. Okay, so this may be a propagation delay. Most probably this may be a propagation delay. This TD may be a propagation delay, and this additional delay may be due to a reflection. Okay, like this. Okay, so if we have a base station and if we have a user, one signal is coming like this, another signal have a is a reflected signal. So these two signals are represented here. One signal have just a delay, that is a propagation delay. This signal, this is an electromagnetic signal. So from here to here, it is traveling. So this is traveling time. Okay, so it is propagating. So this is propagating time, propagating delay. Okay, and this additional delta t introduced may be due to this reflection. Okay. Okay, so we will try to try to find the input and output relationship of this channel. Okay, so we know that we have transmitted xt, okay, and that xt is delayed here. So here we have x t minus td, because this transmitted signal is delayed, this part. Okay, so this is this part, maybe that is xt minus td. Okay, and due to this delay, so here you can see that it is also attenuation. No? Attenuation factor is there, gain factor or something. Okay, so that happened because of this reflection or something. Okay, we don't know. Okay, but we can just imagine. Okay, so here here you have also xt, the received signal. Okay, and it is traveling through this path, and first it has the scale factor. Okay, so first our transmitted signal will be multiplied by this factor alpha xt. Okay, then that alpha xt has a delay, and delay is td plus td. So we have here alpha x t minus td plus delta t. Okay, td plus delta t. So here we have, so output of here, this signal, output of this total system, this path, okay, will be alpha x t minus td plus delta t. Okay, so this is the delay, no, like this. Okay, so you can see that at the at the received end or at the user, the both signals are added, no? So there is a sum of these two signals. Okay, so we can say that the output signal by t is equal to x t minus td plus alpha x t minus td plus delta t. Okay, so this is our input and output relationship of the signal. So that relationship we can get using the given data. Okay, or if there is no given data, we can use physics law to get this input output relationship. Okay, now we need to, so we have input and output relationship, and we need to find the transfer function, no? So because we are dealing with the transfer function here. Okay, okay, so we have to find the transfer function of this channel. Okay, so this is channel. Okay, now this is channel, let's say it is HC. Okay, so this is our channel now. So how to find the transfer function? So as usual, I will get Fourier transform of both sides. Okay, Fourier transform of both sides. Okay, so Fourier transform of yt, say it is capital YF as usual. Okay, so you can see that Fourier transform of two signal, no, two signal, some signal. Okay, so the plus mark is here. So using the linear property of Fourier transform, you can consider separate Fourier transform here. Okay, so this is using linearity property. Okay, and this alpha is a constant, so I will get that alpha here. Okay, and you have x minus td plus delta t. Okay, like this. Okay. Okay, so now I get the Fourier transform. Okay, and you can see that it is again time shifting signal. So, and this one also time shifted signal. So I can write the Fourier transform as e to the power minus j omega. Here the delay is td xf plus alpha is here, and here the delay is td plus delta t. So I can write it e minus j omega. Now my delay is td plus delta t. Okay, into xf. Okay, so if I divide this by xf, okay, so here I have xf, and this xf and this xf will cancel out. So what is this? This is our channel transfer function. So I will put it as hc. Okay, so it is hcf. Our channel transfer function is equal to, here you can see e to the power minus j omega dt, alpha e to the power j omega td plus delta t. And you can see that e to the power j omega td is common for both signal, both terms. So I get out this e to the power j omega td, and I will have 1 plus alpha e to the power minus j omega delta t. Okay, so what is this? This is the channel transfer function of our question. Okay, so this is channel transfer function. Okay, so we have derived the transfer function for channel. Okay, So I am going to use this identity actually. Okay. So here one part I have already derived. Okay. And I have to derive the equalizer response also. Okay. So here I have a equalizer. Okay. So I will get the equalizer. Okay. So I will get the equalizer here. So you can see that this is our equalizer. Okay. So this is our equalizer. So I need to find the transfer function of this equalizer. So I think so here you have the delay and weighted factor. Okay, so these are weighting factor of filters. Okay, these are filters actually. These are filters. Actually, this is FIR filters. Okay, this is FIR filter. Okay, finite impulse response filter. Okay, so this is a filter. Okay. And so first we need to get the we need to find the input output relationship. Okay, so I think we can find the input and output relationship easily. Okay, so I will get this input signal as xt. Okay, as usual. Please don't think that this xt and this yt and this xt and this yt's are not equal. Okay, I just get first I have considered this channel. Okay, this channel, then I have considered the equalizer. Okay, so this is xt is input to the equalizer. Actually this input is the output of channel. Okay, so I will write it as yt. Okay, so here input I will write as yt. Okay, I hope it will not confuse you. Okay, because here we have a channel. Okay, now we have xt and output of the channel is yt, and this yt should be fed to, so this is distorted signal, and it should be fed to the equalizer. No, okay, and the output signal will be distortionless signal. Okay, okay, so let's say it is y dash t or something. Okay, now input of the equalizer is yt, and output of the equalizer is y dash t. Okay, so this is our channel, and this is the equalizer. Okay, so okay, I will consider this as yt. Okay, and output of is y dash t. Okay, so now I will write the expression for this output. I think you can write it easily. Okay, so here yt is given, and you can see yt is multiplied by a naught. So here you have a naught yt. Now here one delay is here. Okay, so here, okay, here output of here, the yt is has one delay. No, so yt has one delay delta t, and it is multiplied by a1. Okay, and here when it come to this filter, okay, it is delayed by 2, no, 2 delta t. So here it is multiplied by a2 y t minus delta t, 2 delta t, no, like this. Okay, so like this. Okay, so I can write this as the output of filter y dash t is equal to, okay, so this is equal to, and you can see that here it is a summer, okay, adder, and all these components are adding to form the output. Okay, so here we have our first component a naught y t plus 1 y 1 y t minus delta t plus 2 y t minus 2 delta t plus a 3y t minus 3 delta t plus so on up to a n y t minus n delta t. Okay, so this is the input and output relationship of the transfer function. Okay, so now I want to find the transfer function for the equalizer. That is, I want to find h EQF, that is the equalizer transfer function. Okay, so to find that transfer function, I will get the Fourier transform of both sides as usual. Okay, so I will get the Fourier transform of both sides. Okay, so Fourier transform of y dash t, the output signal, let's say it is capital Y dash F. Okay, and you can see that so all these terms are adding. Okay, so using linearity property, we can find the separate Fourier transform of each component. Okay, using the linearity property, like we have done here. Okay, like we have done here. So I'm not going to separately write the Fourier transform terms. I will write directly the Fourier transform. Okay, so if I get this term, Fourier transform of a naught yt, I have a naught is a constant, and Fourier transform of yt, that is our input signal. Let's say it is capital YF plus here a1. Now I find the Fourier transform of this term. Okay, Fourier transform of this term. So a1 I can get out because it is constant. Now I have to find the Fourier transform of yt minus delta t. Okay, so you know that this is time shifting. So using time shifting property, we can write it as e to the power minus j omega delta t yf plus this a2 is here, and it is shifted by 2 delta t. So delay is 2 delta t. So here it is shifted by 2 delta t. So I will write it as 2 delta t. And yf is here plus a3 e to the power j omega. Now it is 3 delta t yf. And you will get the terms up to this one. So this is the final component, and we have to get the Fourier transform of that final component. So it is, you know that this an is constant, I get out. So you can see that this is again time shifting signal, time shifted signal. The time is shifted by n delta t. So we have e to the power j omega n delta t 1. Okay. So if I divide all terms by yf, okay, yf, that means all these yf are cancelled, no? Okay, so we have y dash f yf. So this is input frequency domain signal, and this is, sorry, this is output frequency domain signal, this is input frequency domain signal. So output by input means transfer function, no? So that is the transfer function of our equalizer. Okay, so it is, you can see that we can write that as A0 plus A1 e to the power minus j omega delta t plus A2 e to the power minus j omega delta 2 delta t. So I will write it as 2 delta here, delta t plus A3 e to the power minus j omega 3 delta 3. So I get this 3 here. So I have 3j omega delta t and A4 e to the power minus 4j omega delta t, so on up to n. So I have here a n e to the power minus n j omega delta t. So this is the transfer function of our signal. Okay. Now, what is our duty? What is our task? Our task is to find these coefficients for distortionless transmission. Okay, to cancel out the distortion. Okay, to cancel out the distortion, we need to find these coefficients. Okay, so we have to use this property. No? Again, we have to use this property, these two properties for distortionless transmission. Okay, so I will write this equation here again. Okay, I will write this equation here again. Not equation, not block diagram. So we have the channel HCF, and you have the equalizer, and here you have XT, and here you have YT. Okay, and this YT should be distortionless. To be distortionless, this whole system transfer function HF should be equal to K e to the power minus j omega TD. No? Okay. Yes, TD. Is no? Okay. To the power j omega TD. Okay. And we know that this is cascaded signal. This is cascaded signal. Okay. So we have like this. We can have H channel F into H equalizer F, because these two systems are cascaded. So we have to get the product here. Okay. And it is HF is frequency response of this total channel. So this the total system. Okay. So this can be a total system. Okay. Okay. So now this has this doesn't have any distortion. No. So this should be, this HF should be equal or approximately equal to this KE minus j omega TD. Correct? Okay. Minus j omega TD. Okay. Okay. So so we have found this one. No? We have already found this one. HCF we have found. What is HCF? This is, no? So this is HCF for a given channel. Okay, so this is the transfer function for given channel. So I have put that one here. Okay, so here I will use this one. Okay, I will use this one. Okay, so HCF, I have e to the power minus j omega t 1 plus alpha e to the power minus j omega delta t. Correct? Correct, no? E to the power minus j omega td into 1 plus alpha e to the power minus j omega delta t. This is our channel. Okay, so this channel transfer function. Okay, HCF. Okay. So this is our channel transfer function. This transfer function we have found it earlier. Okay, j omega dt 1 plus alpha e to the power minus j omega delta t. Okay, by h q is equal to or approximately equal to k e minus j minus j omega dt. Okay, like this. Okay, so we have this transfer function. Okay, so using this we can say that HEQ, that is our equalizer transfer function, can be equal to, so this part and this part can be cancelled out, so we can say that k plus alpha e to the power minus j omega delta t. Okay, so this is our transfer function, given transfer function. Okay, given transfer function, not given the equalizer transfer function. This is our equalizer transfer function, and that equalizer transfer function for distortionless transmission. No? So this is equalizer transfer function for distortionless transmission. Distortionless transmission. Okay. Transmission. Okay. So this is the equalizer transfer function for distortionless transmission function. The distortionless transmission. Okay. So please note this. Okay. It is very important. So this is equalizer transfer function for distortionless transmission. Okay. How we find it? We find the channel transfer function, and channel transfer function into distortion transfer function should be equal to k e j omega t d if it is not distorted. Okay, for distortionless. Okay, so we can evaluate the HEQ. Okay, so here we have used the distortionless condition. No, HCF HEQF equal to ke j omega td. So that is the condition for distortionless transmission. Okay, so under that condition we have evaluate, we have find the equalizer transfer function. Okay, so this equalizer transfer function is, we can see that it is for distortionless transmission. Okay, so we know the distortion, we know the equalizer transfer function for distortion transmission, distortionless transmission, and also we have derived our general equalizer transfer function. No, that is this one. Okay, for distortionless this transfer function and this transfer function should be same. Okay. So let's say that this is our general transfer function. We have derived using the input-output relationship. Okay. Okay. That is H equalizer F. This is our general transfer function. We have derived using input and output relationship. And this is our distortionless transfer function. For distortionless transmission, then this transfer function and this transfer function should be same. No. So what we have to do? We have to evaluate that coefficients, no, A0, A1 up to AN for distortionless transmission. So if we can equal our general transfer function, this transfer function to this transfer function and evaluate these coefficients, we will have the coefficients for distortionless transmission. No? Okay, so that is the concept here. So yeah, we have to use this alpha is very less than 1, and also we have to use this identity. Okay, so we have one identity. It is expansion. Okay, it may be one of Taylor series expansion, I don't know. So I can write this x minus x. Okay, so we have given this identity is equal to 1 x plus x square plus x minus square up to infinity. Okay, so this x should be very less than 1. So if this x is very less than 1. Okay, so okay, 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 so this is very less than 1. Okay, and it is given that this alpha is also very less than. Okay, so you can see that. Okay, you can see that. So this is k is a constant. Okay, we don't know that constant. What is the value of this constant? It is unknown factor. Okay, this k we don't know what is this k. Okay, and it is said that this alpha is very less than. Okay, so alpha is very less than means this total terms will be very less than, alpha is very less than 1. So this total terms alpha e to the power minus j omega delta t is very less than 1. Okay, so we can get this. Okay, and we can relate this and this with this, can't we? Okay, so here I think, okay, alpha e to the power minus j omega delta t is equal to, I will put the minus here, is equal to minus x. Okay, is equal to minus x, like this. Okay, because this alpha is very less than 1 and this one also very less than 1. Okay, this total value also will be very small number, small value. Okay, okay, and I will be equal it to, I will equal it to minus x. Okay, so here I can write this HQ. So this is for distortionless transmission. Okay, I will put the mark here. It is for distortionless transmission. Distortionless transmission, the equalizer transfer function is k 1 by 1 alpha e minus j omega delta t. Okay, so I have put minus x instead of this alpha e j omega delta t. So I have k 1 minus x. Okay, so this x is very less than 1, very less than 1. Okay, and we can write it using this expansion, that is 1 by x plus x square up to infinity. No, like this I can write. Okay, so this is x1, x2, x3, so on. Okay, so here x is equal to minus alpha e to the power j omega delta t. Okay, so I can write this HEQ. Okay, that is for distortionless transmission, as the k is here. Okay, 1 plus here the x, no, so x is minus x is equal to alpha e to the power j omega t, so x is equal to minus alpha e to the power j omega t. So here I have minus, no, minus alpha e to the power j omega delta t. Okay, now x is square, so that means this x is square, so I have square this minus alpha into e to the power j omega t square. That means I will get the plus value, so here I will have a plus value, no, alpha square e to the power minus j, so this one also is square, so that means I have 2 j omega delta t. Okay, and I have x square, no, x to the power 3, that means I have minus. Okay, minus alpha 3 to the power, here the e to the, it is also, we have to get the e to the power 3 value, so e to this also have e to the power 3 value, that means we have e to the power 3j minus, okay, minus 3j omega delta t. Okay, and after that you have x to the power 4, that means alpha 4, because I have plus value here, because alpha minus alpha into minus alpha into minus alpha into minus alpha, so 2 I have plus, 3 I have minus, again 4 I have plus. Okay, so I have plus here, plus alpha 4 e to the power minus 4j omega delta t. So okay, so I will have this kind of one, no? So if I equate this transfer function, so this transfer function is for distortionless transmission. Distortionless transmission. So if I for this transfer function, okay, I get it. Okay, I will write it. Okay, so we have derived transfer function. Okay, we have derived transfer function h q. So that is derived transfer function. We have a naught plus a1 e to the power j omega delta t plus a2 e to the power minus 2j omega delta t plus a3 e to the power minus 3j omega delta t. So a naught is equal to this, no? A1 is equal to this, and a2 is equal to this. Okay, so I can write as this a naught equal to k, because k factor is here. 1 is equal to alpha k, and a2 a1 is equal to minus alpha k, a2 is equal to again plus alpha square k alpha square, a3 is equal to minus k alpha to the power 3, a4 is again plus k alpha 4, a5 is k alpha 5, and it is minus. So I can go up to an, no? An I have plus or minus, we don't know, it is depend on this n value, plus or minus k. Okay, so we will have an, I don't know, plus or minus k alpha n, correct? So likewise, we can find the coefficients in order to have a distortionless transmission. So this coefficients is for distortionless transmission. Distortionless transmission. I hope you have get an idea. Okay. So we can see that we can equate this transfer function to general transfer function if this alpha is very less than 1. So the alpha should be very less than 1 to have a distortionless transmission. This alpha should be very much less than 1 to for having a distortionless transmission. Okay, so we can show it, we can say that one, and also we can evaluate this AI, okay, to have this this condition. So this condition is for distortionless transmission. Okay, so I hope you can get the idea. Okay, but this derivation not required for the answer. Okay, this derivation I hope this derivation should be needed. Okay, this derivation only should be needed to find the AI. Okay, this derivation is needed for. Okay. So general, you have to find the general transfer function for this tap delay equalizer. Okay, to evaluate to find these coefficients. Okay, other derivations are not required because also are given, no, because this HEQF is equal to 1 plus alpha e to the power j5 del f delta t. So here I have used omega here, but 25f is equal to omega. So instead of this 25f, I have used omega. Okay, so don't get confused. Okay, so the both terms are same. Okay, instead of f, I have used omega. 25f, I have omega. I have used omega. Okay, so this is for distortionless transmission. Okay, and here here for this question we are given this k is equal to 1. No? According to this question, this k is equal to 1 actually, because this is already given. Okay, so you can see that we have derived this one. Okay, we have derived this one. Okay, so I hope you have the idea how to derive this, how to get this. Okay, but it is given in the question. Okay, and this k is equal to 1 because it is given as HEQF is equal to 1 by 1 alpha e to the power minus j omega delta t. So in the question this is given. Okay, so this is for distortionless transmission. Okay, so we have given this one. Okay, so using this identity. Okay, so we have given this one. Okay, so we have given this one HEQF 1 by 1 alpha e to the power minus j omega delta t. We have given this. Okay, so here we have derived it generally for general case. Okay, so we have this k factor. Okay, but for this question k is equal to 1, so here we have 1 only. Okay, so this is given. Okay, so this is given already. Okay, this one given. Okay, and we can use that identity minus x is 1 plus x is square is 3 to write this in terms of like this. So we can write it as 1 plus 1 minus alpha e to the power j omega delta t plus alpha square e to the power minus j omega 2 delta t plus minus alpha 3 e to the power j omega 3 delta t, so on. We can use this identity to write this. Okay, so you have to simply write this, and then you have to derive this one. You have to derive this one. Okay, and you have to equal both the terms, no, both identity. Here again you have this is equal to 1 plus a naught e to the power j omega delta t plus 1 e to the power minus 2j omega delta t plus a3 e to the power 3j omega delta t. So you have to equalize these terms. On here you don't have 1 here, so you have equalize these terms, no? Like this, so you will get. Okay, so in the question it is very easy, but we have done all the derivation also here. So I hope you could understand this one.